Hello and welcome to our lesson. My name is Themba Ncube. Today we are looking at revising of acids and bases. We want to look at the different techniques in terms of answering questions that are based on acids and bases. Right. Now, let's look at the overview of acids and bases as a component of the broader knowledge area of chemical change. So definitely we will look at the different types of reactions involved in as far as acids and bases are concerned. But more importantly, we would also look at the theories that have to do with acids and bases, which is your Arrhenius Theory, your Bronsted-Lowry. We'll also look at different techniques that have to do with acid-base reactions. But also remember that the quantitative aspects, or the stoichiometry that comes to the types of reaction is something that we also need to try and sharpen up. Now, without any waste of time, let's look at some of the key concepts around acids and bases. So we've identified the two broader theories that have got to do with acids. So if you look at an acid or a base, you can describe an acid or a base based on one of the two theories. One of them is the Arrhenius Theory that says to us that because these reactions of acids and bases are actually in aqueous solutions. So Arrhenius says, an acid is by definition a substance that produces hydronium ions in solution. Why a base is a substance that produces the hydroxide ion also in solution. The second theory of bases that we must remember, which is very, very important, is the Bronsted-Lowry or the Lauri-Bronsted theory. What does it say? It defines an acid as a proton donor, right? And then a proton is your hydrogen ion, in a solution, but also a base is a proton acceptor. So these are the two theories that are very, very important. What else? We also want to talk about, remind ourselves also of something that relates to the strength of the acid. There's a big difference between strength and concentration. So when we talk about strength of a substance, be it an acid or base, it has to do with the extent at which it dissociates. Okay. Now weaker acids, they dissociate partially, while stronger acids they dissociate completely in solution. So these reactions actually occur in solution, right? So the pH value, right, which is the pH scale from 0 to 14 of an acid is an indication of its strength, right? So an acid with a pH value closer to 0 is stronger, is that of a stronger acid, while that is closer to 7 but less than 7 is a weaker acid. And then the extent of ionization determines again the strength of the acid, as we have indicated. But also strong acids, they ionize completely, while weak acids, they ionize partially. So that's how we classify acids with respect to their strength. Right. Now let's look at the strength of a base. So the pH value of a base is an indication of its strength. So pH value closer to 14, strong base. pH value closer to but greater than 7, weak base. Right. This is per the pH scale. And then the extent of dissociation. Okay. Now this brings us to another very important point. Bases, they dissociate, while acids, they ionize. That's very, very critical in terms of describing the strength of these acids and bases. Right. And then also we are saying that the extent of dissociation of a base is an indication of its strength. Strong bases, there is complete dissociation, while weak base, there is partial dissociation. Very, very key. Right. Now let's look at typical exam problems, but multiple choice is a very, very important type of a question that we need to familiarize ourselves with, and also try and adopt the necessary skills in terms of the approach to responding to questions of this nature. Right. So pay careful attention to some of the techniques that we will make particular reference to, so that you can also try and use that, so that you practice and become more comfortable in as far as responding to multiple choice problems. Right. So the first question says, consider a redox reaction we're going to underline the key words. So the word redox suggests that this is a type of reaction which involves the transfer of a proton based on a particular theory, okay? So we've got ammonia plus X. X is unknown, and then we get the ammonium ion plus the hydroxide ion. So they're saying here, in the above reaction, X represents what? Right, so we need to look at the products, okay, and then make and say, okay, if we've got ammonia, what could be X if we are to get an ammonium ion? So X actually gives a hydrogen ion, okay, or a proton to ammonia. So a substance that is a proton donor becomes an acid. So anything that has to do with a base is out. So we're going to eliminate the destructors. So anything that has got to do with the base, we eliminate. So we're left with two possible options, okay? So it says water can act as an acid, okay, because it is actually donating protons. So if we say H2O, we are happy to say that if X is a proton donor, it results in the hydroxide ion after donating the proton. So it gives us option A, okay, as the correct answer. Right. Now let's go to the next one. It says, consider the equation below. We've got carbonic acid plus water to give us a hydrogen carbonate ion plus a hydronium ion. Okay, so Bronsted-Lowry bases. So the theory here is about Bronsted-Lowry. Okay, an acid is a proton donor, a base is a proton acceptor, which is some of the concepts that we try to remind ourselves of. Okay, so we need to bear that in mind. So the key words in this statement is the theory itself, which says Bronsted-Lowry. Now let's look at the second multiple choice question. Consider the equation below. We are given a reaction between carbonic acid and water to give us hydrogen carbonate ion and hydronium ion. So the question says the Bronsted-Lowry bases are, right, so I'm going to underline Bronsted-Lowry. Now, this is about the theory of acids and bases. Now, we need to remind ourselves once again, what are Bronsted-Lowry bases? These are proton acceptors. So once we know that, we are able to apply that knowledge. Now, we are saying bases are proton acceptors, right? So if a base is a proton acceptor, let's consider this reaction. Let's identify the bases with respect to this description in terms of the Bronsted-Lowry theory. So if you look at carbonic acid, it acts as an acid because it donates one of its hydrogen atoms to give us that, okay? So this is an acid, right? Meaning that, because this is an acid-base reaction, meaning that water acts as a base. Why? Because it accepts a proton, okay? So water acts as a base. So when water accepts, it gives us the hydronium ion, right? So if water is a base, it means that the hydronium ion becomes an acid, right? It means then in the reverse reaction, the hydrogen carbonate ion is a base. Now the question demanded that we identify two bases, a pair of bases in this reaction. So what do we have? We've got water as well as the hydrogen carbonate ion. So based on that, we can say D is the correct answer. But how did we arrive at that? We first try to understand in terms of the theory which substances are proton donors and which ones are proton acceptors. Right. Let's look at the next one, which says which one of the following pairs of reactants, right, will produce salt, water, and carbon dioxide. This takes us back to the types of reactions, right? Now, any acid-base reaction produces salt and water, okay? So the formation or the production of salt, has a wide range of reactions. So in this case, the question specifically wants us to identify a pair of reactants that are going to react to give us salt, water, as well as carbon dioxide, right? So we're going to interrogate each one of them and see which one gives us salt, water, and carbon dioxide. Now, if you look at reaction A, first of all, for us to get carbon dioxide, one of the reactants must have carbon and oxygen. But then if you look at the reaction between zinc and sulfuric acid, it's a typical reaction between a metal and an acid. This gives us salt and water. So there is no way we are going to get a gas in this case. So we're looking also for a gas-forming type of a reaction. Now, if you go to option B, it talks about a base and an acid. So this is going to give us a salt and water again, right? This will give us salt and water. Still, it doesn't give us what? Carbon dioxide. So we'll eliminate that option, right? Now, if you look at the remaining two options, the reaction between a metal oxide and a sulfuric acid, or an acid for that matter, there is no way we can get carbon dioxide in this case, right? So we'll remove that option as well, right? And then also, if you look at the remaining option, which most likely is the correct answer, this is a metal carbonate, right? That's a metal carbonate which reacts with an acid. Okay, this is definitely going to give us what? A salt plus water, as well as carbon dioxide, because that's what distinguishes it from other reactants in the given options. So this is a typical gas-forming reaction, if you can come to think of it. Then this says to us that D is our correct option. So these are some of the few examples that we've used, but the main thing that we want to take home from these multiple choice is the technique, the approach in terms of responding to this type of question. So knowing the concept involved, highlighting the keywords in the question or in the statement, it will also serve as a guide in terms of eliminating the distractors and as well as coming up with the option that is correct. So it's not a typical way of shooting in the dark and taking a wild guess. So you need to apply the knowledge that you have in trying to identify the most correct option. That said, we'll take a short break for now. When we come back, we'll look at more type of reactions in terms of revising acids and bases. Let's take a short breather for now. Welcome back to our session. We're still looking at, our revision based on acids and bases. Right, now we'll take a turn to look at questions that are structured, your typical section B, questions, and see how best you approach those questions and how exactly you use some of the knowledge that you've learned in as far as acids and bases to apply that knowledge. Right. Now, the question says, sulfuric acid, the formula is given, H2SO4, okay? It reacts with water through a multi-step reaction. So we've got reaction 1 and reaction 2, right? Okay? Now, the first question says, is water acting as an acid or base in reaction 1 and 2? In reaction 1 and 2. So let's try and interrogate the role or the type of substance water is in the two reactions that are given. This is also based on the theories, right? Okay, but which theory is this exactly? This has to do with the Bronsted-Lowry, right? So this is the Bronsted-Lowry theory, okay? So Bronsted-Lowry theory defines an acid as a proton donor, okay? While it identifies a base as a proton acceptor, okay? Simple and straightforward. So in an acid-base reaction based on the Bronsted-Lowry theory, there is a transfer of protons. So there is a donor-recipient type of a relationship. So if we look at reaction 1, water actually accepts a proton, right? So the proton moves from the acid is transferred from sulfuric acid to water. Okay, so in this case, water acts as a proton acceptor, hence it is a base. Okay, similarly, the hydrogen sulfate ion, also donates a hydrogen ion. So in both cases, water acts as a proton acceptor, right? So for that reason, we can simply say that water acts as a base in both reactions. Why? Because according to Bronsted-Lowry, in both reactions, water is a proton acceptor, right? Okay, so we've agreed that this is a base in the first reaction as well as in the second reaction. Why? Because in both cases, when water accepts, it gives us a hydronium ion. Okay, so similarly in the second reaction. So that's the kind of knowledge that we needed to be reminded of, right? Okay, then the follow-up question says, write down the formula of a substance that acts as an ampholyte in the given reactions. Okay, take note, it says reactions. This suggests that we're talking about both reaction 1 and reaction 2. And then after that, we're supposed to justify our choice, right? Okay, so if you look at this question, the key term or the key word in this question is ampholyte. Then we need to ask ourselves what an ampholyte is. You know, in the context of acids and bases with respect to the transfer of protons, there is a proton donor, which is an acid. There's a proton acceptor, which is a base. So an ampholyte is typically that substance that can act as an acid or a base in different reactions, right? So now if we look at the first reaction, we say sulfuric acid is an acid, right? While water is a base. So this is an acid plus base. So when water accepts, what does it give us? It gives us a hydronium ion. So this hydronium ion becomes a conjugate acid, right? It means in this case, the hydrogen sulfate ion is a proton acceptor in the reverse reaction, hence it's a base, right? So the hydrogen sulfate is also still an acid because it donates, while water, we've identified that it is a base, right? So when water accepts, what happens? It forms a hydronium ion. So when this happens, it means the hydronium ion is an acid in the reverse reaction, or it's a conjugate acid, and then the sulfate ion is a base. Right. Now, if you look at the hydrogen sulfate ion, in reaction 1, it acts as a base, but in reaction 2, it acts as an acid. So simply, it means that the substance HSO4 minus is an ampholyte, okay? Because in one of the reaction, it acts as an acid. In the other reaction, it acts as a base, right? Okay, now we move on to a different question that has to do with types of reactions, right? It says, write down a balanced equation of reaction between sodium hydrogen carbonate, the formula is given, okay, and sulfuric acid, also the formula is given. So the key thing here, we need to understand that what type of a reaction is this in the first case? This is a metal carbonate plus an acid. So it's a type of a reaction. So what are our reactants? Our reactants is sulfuric acid, H2SO4, right? Plus sodium hydrogen carbonate, okay? To give us a salt. The salt that is going to be formed here is sodium sulfate. Okay, sodium sulfate, take note of the formula, SO4, okay, plus carbon dioxide plus water, okay? So this is like salt, this is a reaction that is used in the formation of salt. Salt plus carbon dioxide, okay, carbon dioxide plus water. Right. Okay. Now the balancing part comes in. If you look at the sodium on the right-hand side, it's 2 atoms. So we can also put the 2 moles there. Okay. That would kind of change also the number of carbon atoms. On the left now it's 2, and then on the right we still have 1, so we can put a 2 there. Okay. What about the hydrogen? How many hydrogens do we have on the left? It's 2 from the sulfuric acid and 2 from the sodium hydrogen carbonate. It means we can also put a 2 there. So if we can check if indeed our reaction is balanced, I think it would also give us the stoichiometric ratio in which these substances react with each other. So a mole of sulfuric acid reacts with 2 moles, right, of the sodium hydrogen carbonate to form 1 mole of the salt, 2 moles of carbon dioxide, and 2 moles of water. So we can also put an arrow there. So what does that arrow tell us? Because our focus is on the type of reactions, we want to appreciate that this is also, we can think of this as a gas forming type of a reaction, right? So this has a lot to do with the chemical formula and, you know, the whole stuff in terms of balancing, right? Okay, so we have, I managed to attempt that. Now let's look at the other question, which says, consider the following balanced equation. Now this equation has been balanced for us already. Now we are saying we don't need to temper around, you know, the stoichiometry in terms of, you know, the stoichiometric ratio in which they react. So we can simply interpret because it has been balanced for us. Okay, but the main focus in this question, it says, identify the type of reactions and give a reason in to support your answer, right? Okay, so let's look at the first one. The first reaction, it forms a salt. Let's take it from that end. It forms a salt, water, okay, plus carbon dioxide. Okay, so we were trying to work backwards. If a salt is one of the product formed, it means that an acid should have been you know, one of the reactants. So would identify sulfuric acid as an acid, right? Okay, but for us to get carbon dioxide, here we also want to recognize that this is a metal carbonate. Zinc is a metal carbonate. Okay. Now, we also want to say, okay, this is a type, what type of reaction forms salt? We know these are acid-base reaction, okay? So this is an acid-base type of a reaction. How did we arrive at that? We looked at the type of products and worked backwards in terms of the reactants so that we can be able to classify this reaction. But also, even if you keep track of the oxidation numbers, zinc is +2 on the left and +2 on the right, okay? Also, you look at the sulfate is still the same, okay, also in that case. So as a result, this can be a redox reaction. It's an acid-base reaction in terms of proton transfer. But the easiest way to classify this is to look at the products and work backwards to try and identify the types of reactants so that we are able to arrive at the type of reaction. So this is typically an acid-base type of a reaction. Right. Now, we've got another type of a reaction, and we want to also try to think about the reason why we would classify this reaction as a specific type. Right. So this is a reaction between a metal, okay, and an acid. Right. This is a reaction between a metal and an acid. We are getting a salt, okay, plus hydrogen gas, okay. But what is important here is that we need to also keep track of the changes in the oxidation numbers of these substances, right? So what are we saying here? We are looking at zinc, its oxidation number is 0. Now we're going to apply the rules of assigning oxidation numbers. So there's a whole lot of knowledge that we have gained that we need to bring to the fore and try to apply so that we make sense of this scenario, right? So if we look at zinc for argument's sake, this side zinc is +2, right? It's +2. And then also, if you check, the zinc undergoes, you know, loss of electrons in this case. While if you check the sulfate ion, in this case, the sulfate ion is a spectator because its oxidation number does not change. So we can represent the change in the oxidation number of zinc using a half reaction. So this is going to be zinc to give us what? Zinc, okay, just to correct that. This is going to give us zinc 2+, okay, plus 2 electrons, okay? Now, immediately we are thinking this has to do with loss of electrons. So this is oxidation, okay? This is an oxidation half reaction. We're onto something now. But if we look at hydrogen, in this case, the hydrogen is 2 plus, okay? So it's 2H plus, okay? These two of them, okay? Plus 2 electrons, okay? Because the oxidation number of hydrogen in its molecular form is 0. It means these hydrogen ions, they gained electrons. What does that give us? It gives us H2, okay? Now, there is a transfer of electron from zinc to hydrogen ions, right? So this is a reduction half reaction, right? Okay, so definitely, once we have got oxidation and reduction, this gives us a redox reaction, okay? Why are we saying this is a redox reaction? Because this involves a transfer, okay, of electrons, okay? This involves transfer of electrons. Hence, we have managed to arrive at the oxidation and the reduction half reaction. So over and above, you know, the transfer, we managed to keep track of the changes in the oxidation numbers. So this is definitely a redox reaction, and the reason for that is that there is a transfer, which is loss and gain of electrons. Right.
Is he writing up?
Welcome back to our session. We are looking at revising acids and bases. Now we'll look at different types of questions and also try and emphasize on the technique, you know, and how we apply the knowledge that we've gained in as far as chemical change, but with particular reference to acids and bases. Right, the question reads, a few drops of bromothiamyl blue, okay? So this is an indicator added to a potassium hydroxide solution in a beaker. A dilute sulfuric acid, all right, solution is now gradually added to this solution until there is a color change, right? So in trying to unpack this problem, we understand that the reaction is between potassium hydroxide, which is a base, and a dilute sulfuric acid solution, which is an acid. So typically, in terms of the type of reaction, this is an acid-base reaction, right? Okay. So if we have an acid and a base, what do we expect to get from this reaction? We're getting a salt and water, right? Okay. Then the question says, what type of acids and bases are present in this reaction, right? So if we can go back to that, we are looking at the type, right? Now remember, we've got weak acids, strong acids, weak bases, strong bases. So this question precisely is demanding of us to say, are we able to identify, you know, a given substance as a strong acid or strong base, or weak acid and weak base? Okay, so but generally the reaction concerned in this case is an acid-base type of a reaction. So it's a pretty much straightforward question that has to do with you remembering the classification of acids and bases. Now, if you look at sulfuric acid as a solution, okay, this is actually a strong acid, right? Now, what determines the strength of an acid, right, is that this acid dissociates completely. So in solution, sulfuric acid dissociates completely, okay? So there's complete dissociation, right? And then we also have potassium hydroxide, right, which is a strong base, right? Now, why is it a strong base? We know that all strong bases, they ionize completely in solution. Okay? So complete ionization and complete dissociation are the characteristics that we use to identify the acid and base in this particular reaction, right? Okay, then the question goes on and says, write down a balanced equation for this reaction, right? So the reaction is between sulfuric acid and potassium hydroxide, okay? So if, say for argument's sake, we have appreciated that this is an acid, okay, plus base, right? What does it give us? Generally, it will give us a salt, okay, plus water, right? So this is an acid-base type of a reaction. So the formula of the reactants in this case have been given. So we just copy them because these are our two reactants, and then that's the salt and the water are molecules that are formed. So now the question is more about balancing in this case. Now, if we look at this equation, if you look at potassium on the right-hand side, it's K2. So we need to put a 2 there, right? And then we check the hydrogen. Hydrogen on the left, it's 4, right? 2 from the sulfuric acid, and then 2 in potassium hydroxide. Then we can put a 2 there. So the stoichiometric ratio in which they react is a mole of the acid reacts with 2 moles of potassium hydroxide to form a mole of the salt and 2 moles of water. So this is the balanced equation. So if there are going to be any questions that have to do with the stoichiometry, so this stoichiometric ratio comes into effect, then we can able to actually apply it, right? Okay, and then it says here, what color change occurs in this reaction, right? Now, if we talk about a change, we must first recognize that the few drops of bromothiamyl blue are added to the potassium hydroxide solution in the beaker. So initially, we need to ask ourselves, what's the color of bromothiamyl blue in the presence of a strong base, right? Because this is a strong base plus strong acid reaction, okay? So this is strong acid plus strong base, okay? Type of an acid-base reaction, because this is what is important in us coming up with a suitable choice of the indicator for this reaction. So in the presence of a strong base, bromothiamyl blue will be blue in color, okay? So the initial color is blue. So as we continue to add a solution of dilute sulfuric acid, there will be a color change when this neutralization reaction takes place, okay? So this is a neutralization reaction, okay? Okay. So when the resulting solution becomes neutral, there is a color change of the indicator. So the color change will change from blue to pale green, right? So if the solution is neutral, the color of bromothiamyl blue is pale green. Why are we saying the color change is from one color to the other? The question says, what color change? So we need to recognize that the few drops were initially added into the solution of potassium hydroxide. And then we asked ourselves a question to say, what's the color of bromothiamyl blue in the presence of a strong acid? It's blue in color. So if we continue adding the acid, a reaction, neutralization reaction does take place. So when the resulting solution becomes neutral, what's the color change that's going to happen? It's from blue to pale green, right? So that's how we arrived at that. Okay, and then so the color of bromothiamyl blue in a strong base is blue, okay? And then as we continue to add, and then when the resulting solution is neutral, it will be green. So it's from blue to green. That's how we arrived at that, right? And then the question goes further and says, a few drops of bromothiamyl blue are added to the beaker. A diluted solution is now gradually added until there's a color change. So that's when we arrived at the pale green. What color change occurs in this reaction? We're able to say from blue to pale green. And then the follow-up question says, a few additional drops, right, of the acid. Now we're adding more and more acid into the beaker. Now the solution is already neutral. Now we continue to add more acid. It means that in that container, there is more of the acid. And then it says, and the color of the solution changes as we add additional drops of the acid into the solution. Now, what color change occurs now? Now we have to go back and say, if you have an acidic solution, okay, and then there is bromothiamol blue, what color is going to be observed? So remember, we started with blue, which was the color of the indicator, bromothiamol blue, in the presence of a strong base. When neutralization occurred, the solution turned pale green. But then the question says, we kept on adding more and more acid. It means now the resulting solution becomes more acidic. Now the question is, what color is bromothiamol blue is change in terms of, a strong acid? So we understand that what is going to happen is that in the presence of a strong acid, the bromothiamol blue changes to yellow. So that's the color change, right? Okay, so, and then it says here, this color change, actually, it will change from, we're saying, from neutral, which was pale green, okay, to yellow. Okay, that was the color change that takes place. And then, obviously, this is our balanced equation for the neutralization reaction that would have occurred, right? And then the last question says, name the salt, right, that is formed in the reaction represented by the balanced chemical equation. So we said it's acid plus base, strong acid plus strong base, to give us a salt, okay, and water, okay? Now, the question says, name, okay, be careful, they can be name or formula, or both. In this case, we are able to identify that this is the formula of the salt that is formed. So we go back to chemical formula and naming compounds. Then we are expected to actually give the name of K2SO4. So the appropriate name for this salt is potassium sulfate, right? So that's the name of the salt that is formed. So that's basically some of the concepts that are very important in terms of responding to questions of this nature, right? Right, we'll take a short break for now. When we come back, we'll look at more of the structured questions on revising acids and bases. See you after the break. Welcome back to our lesson. We are still revising acids and bases. Now let's look at another type of structured questions which involve a lot of stoichiometry, which cuts across in any of the problems that have got chemical reactions. Right. Now, in this case, we've got anhydrous oxalic acid. Now, anhydrous suggests that there is no water of crystallization in these granules of oxalic acid, whose formula is C2H2O4. It's a good primary standard. And if we talk about a standard, what are we talking about? We're thinking a standard solution whose concentration is actually known, okay? And it can be used to standardize the concentration of barium hydroxide. So at the end of the day, barium hydroxide is a base, while oxalic acid, as the name suggests, is an acid. We're given 4.5 grams of the solute, right, are used to prepare a 125 cubic centimeter solution, right? So the solute are granules that will dissolve completely in water in that given volume. So the question says, calculate the concentration of the acid. Now, which acid are we talking about here? We're talking about oxalic acid. Now, remember, if we are to determine the concentration, we know that concentration of a substance is equal to number of moles over volume, right? But we have to first of all determine the moles, and we know that the moles of a substance is equal to mass over molar mass. So as a result, we can safely say concentration is equal to, this is from the data sheet, is equal to mass over molar mass multiplied by volume. Right, so what is the mass of the solid that dissolves completely as we form this standard solution is 4,5 grams, right? Divided by, what's the molar mass of oxalic acid? 90 grams per mole, right? And then the volume of the the solvent that is used to form this solution is 125 cubic centimeters. So it's a homogeneous solution that will be formed. So 125, we convert this to cubic decimeters, we divide it by 1,000, which is 0,125 cubic decimeters. Right, so this is 0,125. Okay. So we are able to determine the concentration. So from there, we can go to our calculator and say 4,5, okay, divided by 90 multiplied by 0,125, right? Okay, so this gives us, we can change that 0,4 moles per cubic decimeter, right? So the concentration of this oxalic acid is 0,4 moles per cubic decimeter, right? So that's how we determine the concentration, right? So be careful when you use the calculator. So in some cases, it will give you the answer as, as a fraction. You are able to convert that to a decimal fraction in terms of, 2 decimal places. Very, very important, right? Okay, and then the follow-up question, it says 25 mils, that's the volume of acid. So we know that the volume of acid that was used, okay, is equals to 25 cubic milliliters, 25 milliliters. I prefer to work with the SI unit. Is if you divide that by 1,000, because 1 cubic decimeter, right, is equals to 1,000 cubic milliliters or cubic centimeters, right? So that volume is 25 mils, all right? Which is equals to 0,025 cubic decimeters. That's the volume. Okay, it's diluted with distilled water to make that concentration, right? So what do we know? We know that the concentration of this acid, we have managed to calculate the concentration and managed to get 0,4 moles per cubic decimeter. Now, that concentration is diluted with an unknown volume of water to give a new concentration of 0,015. So that's why the concentration has decreased, because we have diluted. But what remains the same is actually the number of moles. Now the question demands us to calculate how much water was added to the oxalic acid. So this question is basically about dilution, right? So what is it that we know in terms of dilution? We know that we can use the formula concentration 1, which is the original concentration, volume 1 of the actual acid before we added the water. So when you dilute, we will get concentration 2 and volume 2, right? But what remains the same is the number of moles, right? So concentration 1 is 0,4, right? Multiplied by the initial volume, which was diluted, which is 0,025. We've already converted 25 mils to cubic decimeters. Now the new lower concentration after adding more distilled water becomes 0,015. Okay, now we want to understand what's the new volume. This is going to give us an indication of how much water was added, right? So we can be able to determine the new volume after adding water, right? So we can go to our calculator and say, right, okay, what do we have here? We have 0,04, right, 0,4, right, multiplied by 0,025, right? We divide this by 0,015, which is the new concentration. We're just making V2 the subject, okay? So we'll divide by 0,015, right? What do we get? We get, okay. Okay, what do we get from there? Okay, this gives us 3/2. So this is the new volume as a decimal fraction. The new volume is 0.67, right? 2 decimal places. So this is 0.67 cubic decimeters. Now, if the initial volume was 25 mils, and then the new volume is 67 mils, because this is like 67 milliliters. So how much water was added? So we are saying volume of water added, okay, is actually equal to, V2 minus V1 in a dilution, okay? Right, so the second volume, the new volume is 0.67 less the initial volume, okay, of the solution, which is 0.67 cubic decimeters, and then 0.025, okay? Right, okay? So everything is in cubic decimeters. So if we go to our calculator, what do we get? We have 0.67, okay, minus 0.025. Okay, what does that give us? This gives us 0.645, right? So 0.645 cubic decimeters of water was added. So you can change that to cubic centimeters, but you don't have to. So this is the actual volume of distilled water that was added in the dilution process, right? Okay, and then we've got another one which says 40 cubic centimeters of nitric acid of an unknown concentration, all right, is used to neutralize that volume and concentration of barium hydroxide. So 25 cubic centimeters and 0.05 moles per cubic decimeters are for the base barium hydroxide. So this is the balanced equation of reaction, of the reaction between nitric acid and barium hydroxide, right? So what do we have? What name is given to the technique used to determine an unknown concentration of a solution? Right, the calculations that we've been doing have to do with volumetric analysis, but the technique that we carry out in the lab is actually a titration, right? So this is a question based on remembering. So this is about a titration, which is a technique, right? Okay, and then the question says, calculate the number of moles of base that reacted. Okay, how much volume of the base reacted? 25 cubic centimeters. What is the concentration of the base? 0.05 moles per cubic decimeter. So we want the number of moles of base, so which is the number of moles of barium hydroxide, right? Okay, is equals to concentration multiplied by volume, right? Do we have the concentration? Yes, the concentration is 0.05, right? So the formula is from the data sheet. We copy it, and then we want to find the number of moles. So 0.05, which is the concentration, multiplied by the volume, which is 0.025, okay? So we are able to determine that by saying, okay, 0.05 multiplied by 0.025. This gives us the number of moles, okay? So the number of moles is equals to 1.25 times 10 exponent minus 3. 1.25 times 10 exponent minus 3 moles, right? So that's the number of moles. So this is a routine calculation where you've got the formula, substitution, and the correct answer, including the correct SI unit, right? And then it says here, calculate the concentration of the acid. Now, the stoichiometric ratio in which they react is very, very important. It says 2 moles reacts with 1 mole, right? But how many moles of the base reacted? 1.25, okay, times 10 exponent minus 3 mole, right? While we are saying double the number because 2 reacts with 1. So 2 moles of that will be the number of moles of the acid that react will be actually double those of barium hydroxide, which is 1.25 times 10 exponent minus 3. Okay, so this is the number of moles, okay? Now, we are also told that the volume is that. Now, if we want to find concentration, we know that concentration is number of moles per unit volume of solution, right? So the concentration is 2 times 1.25 times 10 exponent minus 3, okay, divided by the volume, which is 40 cubic centimeters. 40 is 0.04 cubic decimeters. So C becomes, right? So what do we have here? We have got the calculation, 2 multiplied by 1.25 times 10 exponent minus 3, okay, which is double the number of moles of barium hydroxide, okay, minus 3, okay. Okay, we close that bracket, divided by 0.04, okay. Right, so this is the actual concentration of the acid, nitric acid, 0.0625, okay, 0.0625 moles per cubic decimeter. Right. All right, so these are some of the few examples that we have used. So it will be very important for you to try and revise so that you become more comfortable. That's the time we had for today. Goodbye.